Previously we have gone with different components based on how the semiconductors can be used for electronic component fabrication, and based on that we have seen the basics like diodes, and based on diodes we have seen different applications, and after that we have gone with BJT and FETs. Based on these BJTs and FETs, that is field effect transistors, MOSFETs and JFETs, we will be using these components, these semiconductor components, to further implement the complex circuits. So that complex circuits, we will be starting with the operational amplifier. So in this course, basically basics of operational amplifiers we will be seeing here. Amplifiers are also called op-amps. So it is operational amplifier. In short form, it is called op-amp. It is op-amp. Okay. So this is operational amplifier. As its name suggests, it is an amplifier. So these operational amplifiers are the amplifiers that basically takes an input and amplifies it, and after amplifying it they will be providing you the output. That output will be an amplified output. So these operational amplifiers are nothing but a voltage amplifier. It is a voltage amplifier. So these operational amplifiers are the amplifiers that is having very high gain. So here very high gain is obtained. So this high gain is because of different stages. Different stages of operational amplifier. So this operational amplifier is not a single stage amplifier. So this operational amplifier is the amplifier that is having different stages. So once one stage is there, it is cascaded with another stage and then another stage. Okay, so there is like first stage, second stage and third stage. Okay, so different stages are there. So this is an input, and finally we are getting the output. So by combining all the stages, this complete box is called operational amplifier. So it is having different stages. So because of different stages, it is having high gain. Okay, and another advantage is like these operational amplifiers are having very high input resistance and very low output resistance. So we will see what is the advantage of having very high input resistance and very low output resistance. So before that, we will see this is the symbol of an operational amplifier. So this is how an operational amplifier is represented. So here it is having two different inputs. One input is represented by a negative symbol, like it is negative. Another input is represented by positive. Okay, so this input that is having a negative sign is called inverting input, and the input that is having positive sign is called non-inverting input. So as the name suggests, inverting means it will be making sure it is, if it is negative it will be inverting, if it is positive it is non-inverting. That means it is not going to invert the output. So there are two inputs. With respect to that, one output is there. Okay, this is a simplified symbol. If we go with the complex, like this is another symbol. Here the DC supply connections are shown. So these two are the input and this is the output. To operate this, there is two different supply voltages are used. Okay, so this one supply voltage is considered as plus V, another one is minus V. So this plus V is also called plus V saturation. Okay, or this negative one is called minus V, or in negative direction, instead of connecting 0, it is connected to a negative voltage, that is minus V set. Okay, So this is the basic of an operational amplifiers, where this will be representing the symbol, and in most frequently we will be using this symbol only, but internally it is having two different biasings are also there. One is plus V and another is minus V. And this plus V also got plus V set, and another one is called minus V set. And it is fabricated by different technologies. So one of the technology is dual inline package, DIP technology, and next one is like SMT, that is called surface mount technology. So there are two different techniques through which different components of the different components of the operational amplifier will be you can say fabricated on a base. Okay, so that base in these cases is basically a PCB. So PCB will be there. On this PCB, different components will be placed. Okay, so the placing of components will be based on like it is either dual inline package or SMT, that is surface mount technology. Two different methods are there. Okay, so if it is dual inline package, it will be like a rectangular chip will be there, and on the two sides, two parallel rows will be there for their pins basically. Okay, and the numbering of pins. So this is pin number 1 and this is pin number 8. There will be a cut mark, or we call it notch. Okay, along with that there will be a dot. So white dot is there. So where this white dot is there, that will be indicating the pin number 1. Okay, so 1 2 3 4 then 5 6 7 and 8. Similarly here in SMT1, where is that white dot is there, that will be indicating the pin number 1. Here again white dot is there, so this will be indicating the pin number 1. So this is how the operational amplifier ICs look like. Okay, and these operational amplifiers, so some history notes about operational amplifiers. So basically the study of operational amplifiers started around 1947. That is the concept of operational amplifiers coined. But later in 1964, the first integrated IC, that is IC, integrated circuit, is of operational amplifier is designed, that is of IC 702, and later 709, and most frequently the IC 70741. So IC 741 is the IC for operational amplifiers that is most frequently used in standard industry related applications. Okay, so whatever the operational amplifier we will be using basically the IC 741. Even in your practical lab sessions also, you might have gone with the IC 741. So this will be the IC for operational amplifiers. Okay. Next we will see like these operational amplifiers are nothing but a voltage amplifier. So a voltage amplifier means there will be an input and there will be an output, and this amplifier is there. So this amplifier, voltage amplifier is there, so there will be some gain. Okay, so this is basically a voltage gain will be there. So this is V input and this is V output, and gain is supposed represented by A V. So A is for gain and V for voltage gain. So if this is the representation, so we can get from here V output will be gain multiplied by the V input. So this is the basic concept for a voltage amplifier. So this is a voltage amplifier. Their output will be directly proportional to input, and that will be multiplied by a gain factor, that will be the gain of the amplifier. Okay, so from there if we want to find out the gain, we can get like the gain will be AV equals to V output by divided by V input. So whenever we will be talking about the gain, So the gain will be output divided by the input voltage. Okay. So from there also we can conclude an operational amplifier is similar to a voltage gain amplifier, or here again the input voltage is going to change the output voltage. So in other sense we can say this circuit, that is voltage gain, that is voltage amplifier is there. So this voltage amplifier circuit is the circuit that is going to control the output based on the input voltage. Okay, so this is voltage amplifier. So here in voltage amplifier, output voltage is being controlled by the input voltage. So it is nothing but a voltage controlled voltage source. Okay, so this operational amplifier is nothing but a voltage controlled voltage source type of device. Okay. So the next we will see what is an ideal operational amplifier and what is an practical operational amplifier, and before that we will see one more concept. Okay, so here it is a voltage device, okay, or a voltage amplifier. This operational amplifier is a voltage amplifier. So if a voltage amplifier is there, so the equivalent circuit of a voltage amplifier is represented by I'm just representing like how the equivalent circuit of an voltage amplifier is represented. We will be providing some inputs. This is the input voltage. So this basically represents the equivalent circuit of voltage amplifier. If it is a gain, so gain will be multiplied by the input voltage. So whatever input is there, that will be multiplied by the gain. This gain term with an output resistance, and across that the output resistance, output voltage will be taken. So this is the equivalent circuit of a voltage amplifier. So from there, if we can just consider, so R input here is the input resistance and R output is the output resistance. AV, that is the gain of the voltage amplifier. If R input, so as we said, like the operational amplifier is a voltage amplifier, there the input resistance is very high. Suppose if it is an ideal one, so input resistance, suppose input resistance is infinity. If this is the case, then if this input resistance is infinity, then whatever input voltage, that is Vs, we are applying, that will be equal to V input. So V input here will be equals to Vs. So whatever input Vs we are applying, that should be appearing to the input voltage. So this input voltage will be like based on its internal input resistance. This is R input. So whatever internal resistance of this voltage amplifier is there, that will be deciding the input to this block. So this is the internal structure. So you can call it like whatever input we are applying. Okay. So this input should be appearing across this R input, so that we will be getting the maximum of the input we are applying. So for that we need to have the R input should be high. So if R input is high, then only the V input will be equals to applied voltage source. Okay. So if it is not there, this is the case of ideal, but in practical R input is not equals to infinity, but it should be very high. We can call it like R input should be very high than the RS. So from there we can another way we can just see from this part only. So if we want to calculate the voltage across this Ri, then what will be the voltage across this Ri? So this voltage across the Ri will be equals to Ri divided by Ri plus Rs multiplied by the Vs. So this would be your input voltage. So this input voltage will be equals to Vs only when we are having the IR, the input. So this is Ri and this is Ri plus Rs. So Vi should be equals to Vs only when this component will be equals to like 1. Okay, then only this will be equivalent, and this will be 1 only when like Ri should be very high than Rs. Then the Rs component we can neglect, and then it will be represented by like Ri divided by Ri into Vs. So these two will be cancelled out, and then V input will be equals to Vs. So for the case like to have all the input components appearing across the input of the voltage amplifier, we need to have Ri very high, or Ri should be ideally infinity. Okay, and this is the case in case of operational amplifier. And also if we talk about the output resistance, so output resistance should be ideally 0. Okay, so if our output, that is output resistance is 0, then at that time here we can get, for this circuit we can get V output will be equals to whatever, if this R output is 0, so whatever this voltage term is there here, input voltage multiplied by gain, whatever input this is voltage is there, that voltage will be appearing directly across this RL only if R out is 0. So then at that time V output will be equals to AV into VI. This would be there. Okay, but R output is not equals to 0. Okay, then we should select R output such that it is very less than the RL. Okay, so if that is, we can represent R output should be very less than the load resistance. If this is the condition, then whatever the gain of whatever the output voltage should be there, that will be equivalent to AV into VI. Okay, so that output voltage will be equal to AV into VI only when R0 is very less, or R0 is very less than the RL. Okay, so this is our voltage amplifier equivalent circuit representation, and here from this concept we can analyze like the input resistance should be very high, or input resistance should be very high than the internal resistance or the resistance that we are applying to the circuit. Okay, RS. So if input resistance is very high than RS, then whatever input voltage we are applying, Vs, that will be appearing to the input of the voltage amplifier. Similarly at the output part, so output resistance of the voltage amplifier should be very less than the load resistance that we are applying to here. So whatever load we are applying, this load resistance should be very high than R0. Then whatever the gain has been obtained through this voltage gain amplifier, that will be appearing across the load. So whatever gain will be there, So signal gain or the output voltage will be appearing across the load of the circuit. Okay. So this is the basic concept behind the R input and R output. That is input resistance and output resistance. Next we will see just how the ideal and practical operational amplifier is different from each other. So this is the operational amplifier symbol. In that there is two inputs. Negative means inverting, positive means non-inverting. Okay, and there is also the concept of same concept like input, two different inputs, inverting and non-inverting. So in ideal case, we are just saying like ideally the input resistance should be infinity. Okay, so here this is the input resistance. Okay, here this is the block. So this is here the input Z input is there. That Z input is infinity if it is an ideal one. So this is an ideal one. So input resistance basically here is infinity. If it is infinity, that means it can be taken as an open circuit. And the output resistance would be 0. So for ideal case, the Z out is 0. So there is 0 resistance means it is a short circuit. So this is, you can just write here, it is open circuit, and here it is short circuit. This is the case of ideal operational amplifier. Similarly, if it is a practical operational amplifier, then between these two terminals there will be an input resistance. So this input resistance will be some values, it will be having some magnitude, it will not be infinity. Okay, so it is represented by a resistance, that is Z input. And at the output part, instead of being output resistance 0, it will be having some resistance, that is Z output. Okay, so this will be the equivalent circuit in case of operational amplifier. So above that we have seen is the equivalent circuit of a simple voltage amplifier. Okay, so we were discussing about the ideal and practical operational. So this, by structure point of view, we have just seen how the ideal and practical operational amplifier will be represented. Now we will see some characteristics of operational amplifier. So here some parameters we will be seeing, and with respect to that, what will be the case in case of ideal one, what will be the case in case of practical one. So if we talk about different parameters, so if we talk about the voltage gain, so in case of voltage gain for ideal operational amplifier is considered to be infinity, and in case of practical one, the voltage gain, that is AV, that we have seen. So AV will be the voltage gain. In case of ideal one, it will be infinity, and for practical one, it is considered to be 10 to the power 6. Next is input resistance, that is R input, or here it is represented by Z input. Okay, so R input should be infinity in case of ideal one, and for practical case, this input resistance is considered to be 10 to the power 6 ohms or 1 mega ohm. Next is output resistance. So this output resistance is R naught, or here Z out, represented by Z output, Z out. Okay, so in case of ideal one, the output resistance would be 0, but in case of practical operational amplifier, the output resistance is considered to be between 10 to 100 ohms. One more term is there, that is called gain bandwidth product. So gain bandwidth product, that is represented by G bandwidth, GBW. So in case of, we will just see what is the gain bandwidth product. So what happens, it is gain bandwidth, this is represented by, we can like Gain means here in operational amplifier gain we can consider AV, that is gain, and multiplied by bandwidth. So gain bandwidth product is basically constant for an amplifier. Gain bandwidth product is constant. So in case of operational amplifier we are considering like AV, that is gain. So this is your gain. We are considering gain is very high. Gain is considered to be very high. So if gain is very high, gain into bandwidth will be a constant. At that time, if we want to calculate the bandwidth, that will be a constant. Suppose a constant is there, divided by gain will be there. So here the bandwidth will be very low as the gain is very high. That means this operational amplifier cannot be used for high frequency applications. For high frequency applications, directly this operational amplifier cannot be used. So we will use some different techniques to reduce this gain and increase this bandwidth so that it can be used for high frequency applications. So because gain we have considered is infinity, so gain bandwidth product will also be an infinity. So whatever infinity multiplied by a bandwidth will be infinity itself. So gain bandwidth product is considered to be infinity in case of ideal one, but in case of practical one it is 10 to the power 6 hertz, because gain has no unit and bandwidth is having the unit of frequency, that is, so that's why it is 10 to the power 6 hertz. Okay, and bandwidth, if we consider in case of ideal operational amplifier, so in that case also the bandwidth is considered to be infinity, but in case of practical one it is 10 to the power 6 hertz. Okay, this is the case when gain is 1. If gain is 1, then bandwidth is considered to be infinity. And one more term is like CMRR, that is common mode rejection ratio. So just see here, we will be explaining this CMRR in later slides. Okay, so CMRR in case of like common mode rejection ratio is considered to be infinity in case of ideal one, and in practical one it is 10 to the power 6, or in case of dB it is 120 dB is considered. It is also a type of gain. So in dB we can represent in terms of 120 dB. Another term is called slew rate. So just we are representing here. In later stages we will be knowing like what is this terms are there. So slew rate in case of ideal one is also infinity, but in case of practical case it is considered to be 80 volt per microsecond. So its unit is basically volt per microsecond. So this is the difference between an ideal and practical operational amplifier. Okay, so this is an operational amplifier, symbol is there, and it is having 3 different stages. So in the previous slides we have gone with like it is a multi-stage amplifier, basically operational amplifier. So it is different stages of operational amplifier. So this is circuit. This figure represents basically different stages of operational amplifier. So it is having the first stage. So the first stage represents differential amplifier input stage. So it is having a differential amplifier input stage. The second stage is voltage amplifier gain stage. So second stage is a voltage amplifier basically. The third stage is called push-pull amplifier output stage. So this is an output stage. It is called, this output stage is nothing but a push-pull amplifier is there. The input stage is a differential amplifier. So input stage is nothing but a differential amplifier, and in the middle we are having the voltage amplifier. So voltage amplifier we have seen the equivalent circuit. So in that voltage gain amplifier, before that we are having a differential amplifier. So this differential amplifier is basically used to have high input resistance, and this push-pull amplifier is considered to be an output stage that is providing a very low output resistance. So there are different advantages of these three stages, and by combining all these three stages we are able to obtain the operational amplifier that is going to provide a very high input and very low output resistance. There are different mode of operation of these operational amplifiers. Okay, so different mode of operation means these can be operated based on the application of input voltage to their input terminals. So there are different mode of operations. One of the mode is like this one. It is called, so here we can see from figure A and B, like at one of the input terminal there are two input terminals. So any of the input terminal we are going to apply an input voltage. So here we are having two different input terminals. So in that, if any one input terminal is going to be used for applying the input and another one is grounded, so here also this is the negative, that is called inverting input. So inverting input is applied and the non-inverting input is 0. In the other case, non-inverting is having an application of input and inverting is having connected to 0. So this is called, this type of configuration is called single ended. So similar is the case like if two inputs will be connected to both of the input terminals, that is called double ended. So this is single ended. So in this single ended, if the input is connected to the inverting terminal side, so this is called inverting. In single ended, overall this is called single ended, but if we are connecting the input to the inverting side, it is called inverting amplifier. So what is the meaning of inverting amplifier? So inverting amplifier meaning means whatever the output is there, so output will be negative of the gain. So if this is having a gain AV, so gain multiplied by the input. So this is the inverting amplifier. So if we are applying the input to the non-inverting side, so this is called non-inverting amplifier. So it is non-inverting amplifiers. At that time the output will be related to AV with input. So one thing we can note here from, so this is one of the terminal, this is another one. So what is the voltage difference between these two terminals is called the input here. So input is not only the input that we are applying, it is the input between these two terminal difference. So here input will be between V input that we are here representing. This is between the voltage difference between these two terminals, these two input terminals. Okay, so if we find out the difference, so this Vi will be nothing but the positive side. So positive side is connected to 0 and the negative side is connected to V input. So it will be V input. So V input is here will be equals to minus of VIN in for this case. So for this case, if we calculate the same Vi, so Vi for this case will be, Vi will be the positive side voltage, that is VIN, minus the negative side is connected to 0, so it will be 0. So the difference of these two is considered to be the V input. So V input here is basically VIN. This is the case in case of inverting, non-inverting. Okay, so that with respect to that only the output has been defined. So the basic idea for the output is V output will be, so the V output should be equals to gain multiplied by the V input, but V input in case of inverting will be minus V in, so that's why it is minus V in. So this is the single ended. Okay, so a double ended is there. So if we are applying the input at both the terminal, so here the input voltage will be the Vi, the difference between these two. So this is the equivalent circuit here. So input voltage in this case will be the difference of these two. So this is positive side, this is negative side. The difference will be like V input 2 minus V input 1. So input voltage will be difference of these two. So based on that, the output will be the gain multiplied by the V input, that is the difference of these two. So V input, so V input will be represented by this. So this is the case of double index. Another one is like this one. This is called common mode. So common mode means here both the inputs are applied with same input voltage. So V input is here and V input is here. So when V input is equals to VIN minus VIN. So if this is the case, this is called the common mode. So if common mode is the case, the output should be equals to 0 because the V input will be difference of these two. This is V input. So output voltage will be gain multiplied by V input. So V input is nothing but V input minus V input. So both are having the same input. So the difference of these two will be equals to 0. That means we are applying the 0 input. So if we are applying the 0 input, the output will also be a 0. So that's why this is the 0. This is called common mode operational amplifier. So these are the different modes of operational amplifiers. Next we will see like how these operational amplifiers with different modes are going to have different output. So we have seen the different modes, so we can just represent. So suppose this is the operational amplifier. Okay, so this is like V2 is there and this is V1 is there, and this is a negative and this is positive, and the gain is AV and here output is V output. So with respect to that, the input voltage will be the difference of these two is called input voltage. So if we see the case like here itself, there are different input output combinations are there. So if we are suppose we will just see different combinations of input and output. So different combinations are different cases. So if case 1 is there, so in that case suppose V1 is equals to 5 microvolt and V2 is equals to 0. If V1 is 5 microvolt and V2 is equals to 0, at this time the output will be gain multiplied by 2, whatever that is, the 5 minus 0. So V output from there we can just see. So V output will be equals to gain, whatever gain is there, multiplied by the difference of these two. So positive minus negative 1. So this is negative and this is positive 1. So V1 minus V2. This will be the expressor. By putting the values we can get like V output as gain multiplied by 5 microvolt minus 0. So it is like something positive value is there. So from there the V output will be coming out to be greater than 0. So if this is the case, V output is greater than 0. If suppose the case second is there, V2 is equals to 5 microvolt and V1 is equals to 0. At that time by putting the value, so V1 will be 0 and V2 will be 5. So it will be minus multiplied by the gain, that will be the minus. So here the output voltage that we will be getting is negative. That means output voltage is less than 0. Okay. Similarly, if third case we consider is like, in that case what will be the output? So output expression we know, this is the expression AB multiplied by V1 minus V2. So V1 minus V2 will be AV multiplied by V1 minus V2. So it will be 5 minus 10. So it will be a negative. So this is negative. So overall we can call it here the V output will be a negative voltage. So V output is negative means we can write like V output should be less than 0.